So, Jai Hind to everyone. I am Dr. Karunesh Srivastava and I am going to discuss about the waveguides for the subject microwave and radar engineering, which is useful for 7th semester and electronics and communication engineering branch. First of all, what is transmission line and how they are classified? Basically, the transmission line is classified in two part, that is geometrical and electrical. So, in geometrical multi-conductor and versus single conductor, and in case of electrical TEM mode or non-TEM mode we can classify. So, multi-conductor, example of multi-conductor is coaxial cable, twin lead line, parallel plate line, strip line, etc. And in single conductor waveguides, and non-TEM, that is T mode, TM mode, HEM mode, etc. So, this is the figure for this waveguide, and you can easily see this. What is the TEM mode? TEM mode is a mode of propagation characterized by electric field E and magnetic field H patterns that are purely transverse with respect to each other, and with the axis of the transmission line or the direction of the propagation. It means Ez and Hz both are 0. A transmission line can support TEM mode if there are at least 2 disjoint conductors in its cross section and the medium filling the cross section is homogeneous, isotropic and lossless. TE mode, TM mode and hybrid mode. What is the TE mode? I have already discussed that here. The transverse electric waves, also sometimes called H waves, characterized by the fact that the electric vector E being always perpendicular to the direction of propagation. In T wave, only the electric field is purely transverse to the direction of propagation and the magnetic field is not purely transverse. In TM mode, transverse magnetic waves, also called E waves, are characterized by the fact that the magnetic vector H is always perpendicular to the direction of propagation. In T wave, only the H field is purely transverse to the direction of propagation and the electric field is not purely transverse. It means Ez is not equal to 0 and Hz is 0 for in case of TM mode. In hybrid mode, in this case, both T and TM waves are coupled together and present simultaneously. In other words, Ez is not 0 and Hz is not 0. Sometimes the hybrid modes are called EH or HE modes. So, these are the modes which will be used in the transmission lines. Now, coming to the appropriate model, this mathematical model gives us the cutoff frequencies and propagation constant for the line. So, for the low frequency we will use the lumped element model, and for high frequency we will use the field model, and the medium frequency distributed element model. In case of low frequency, length of the transmission line is less than that wavelength. In case of high frequency, length of the transmission line is greater than the wavelength. And in case of medium frequency, L is equal to n lambda. So, but a transmission line is generally a few wavelengths long, then it is convenient to extend the lumped element model into the distributed element model. Now, coming to the distributed model, transmission line is assumed to be made up of a series lumped elements or distributed element model, where V and I cannot vary over each incremental length delta z. So, here we have considered the incremental length delta z, and the input current and voltages are the function of length and the time. VZT is the voltage, IZT is the current. So, we have considered here the voltage and current. Now, this is the we can define in the primary constant we can define this transmission line in the distributed element model or lumped element model in terms of R, L, G and C. So, here we can replace this with the help of R, L, G and C. So, the equivalent for this transmission line is R delta Z, L delta Z, G delta Z and so on. So, R and L are connected in series where G and C are connected in parallel. So, the voltage at Z is equal to 0 is our voltage at this terminal is VZT and the current flowing through this transmission line is IZT, and the voltage at distance Z plus delta Z, this is the incremental length of the transmission line. So, at Z plus delta Z, if I consider this node is or this terminal is at Z position. So, if we do the small increment in the length of transmission line, then this terminal will be at Z plus delta Z. So, VZT is the voltage at these two terminals and VZ plus delta ZT is the voltage at this terminal. Now, what will be the current at this terminal? Current at this terminal will be, if the current at this terminal is IZT, and then the current at this terminal will be IZ plus delta ZT. So, now I will define the transmission line equations by using the KVL and KCL. We can write here Vz plus delta V plus Z plus delta ZT minus VZT is equal to R plus L di by R plus Ri, current flowing through this resistance is I, or you can say voltage drop across this resistance is Ri ZT, and the current flowing through voltage across this inductor is L di by dt. So, delta Vz by delta V by delta Z is equal to minus Rizt minus L delta Izt by delta t. Similarly, we can write for the current delta Izt is equal to minus GVzt minus C delta Vzt by delta t. This is the telegrapher's equation, or in case of in phasor form we can write this delta Vz by dz is equal to minus R plus j omega L Iz. We have just taken the Laplace transform of this delta I by delta t. So, this will become S is nothing but j omega. So, I will get here minus R plus j omega L Iz. Similarly, diz by dz is equal to minus G plus j omega C Vz. So, here this is transmission line equation in phasor form, and this is telegrapher's equation in time domain. Now, we can see here this gamma is nothing but under root R plus j omega L G plus j omega C. How will get this propagation constant gamma and characteristic impedance Z naught? Z naught is equal to under root R plus j omega L upon G plus j omega C, and gamma is equal to R plus j omega L G plus j omega C. This is nothing but the combination of or you can say alpha plus j beta, where alpha is attenuation constant and beta is phase constant. Now, gamma is propagation constant, and Z naught is the characteristic impedance. There are these are known as the secondary constant. Gamma and Z naught is known as the secondary constant of the transmission line, and for lossless line gamma should be the imaginary and Z naught is real. Now, at microwave frequencies, it can be seen that the R is less than omega L and G is less than omega C. So, by using the binomial expression, you can find the propagation constant, and they can be expressed as gamma is equal to under root R plus j omega L G plus j omega C, under root j omega square L C. So, here what we have done, we have taken the j omega common from this term, and we have taken j omega common from this term. So if I take j omega L common, so what will I get here? One plus R by j omega L. Similarly, if I take j omega C common, I will get 1 plus g upon j omega C. Now you can see here, this is nothing but j omega square LC under root 1 plus R upon j omega L 1 plus g upon j omega C. So j omega under root LC, by expanding this using the binomial expression, I will get here 1 plus 1 by 2 R by j omega L 1 plus g by 2 j omega C. J omega under root LC 1 plus 1 by 2 R by j omega L plus g by j omega C. So 1 by 2 R under root C by L plus g under root L by C plus j omega under root LC. This is the generalized expression, or you can say after solving these two equations we will get this 1 by 2 R under root C by L plus g under root L by C plus j omega LC. Now what will be the value of alpha and beta? With the help of this we can define, this is nothing but alpha, or you can say we can write propagation constant in terms of attenuation constant and phase constant, that is alpha plus j beta. So after comparing this real and imaginary part, I will get alpha is equal to 1 by 2 R under root C by L plus G under root 1 by L by C. Beta is equal to omega under root LC. So this is the value of alpha and beta after comparing this equation with this. Similarly, we can find the characteristic impedance. At microwave frequency, it can be seen that R is less than omega L and G is less than omega C. So again you will use the binomial expression for getting the value of Z naught. Z naught is nothing but R plus Jx. This is already written here. R plus Jx. So again I will take common L from here and C from here. So if I take L common, I will get here L R plus if I take R common, if I take j omega L common, j omega L 1 plus R by j omega L upon j omega C 1 plus g upon j omega C. So after solving this you will get under root L by C 1 plus R by j omega L ki power half 1 plus j omega C ki power minus half. Now you will expand this under root L by C 1 plus 1 by 2 R by j omega L 1 minus 1 by 2 g upon j omega C. Under root L by C 1 plus 1 by 2 R by j omega L minus g by j omega C. Now this will be equal to R is less than omega L, so we can ignore this. Now we will get here Z naught is equal to under root L by C for the lossless line, for the lossless transmission line. So you can see here this is the real. So characteristic impedance is real for the lossless line, and if I consider the losses, then it will be the complex R plus j omega L under root R plus j omega L upon G plus j omega C. Now let us take an example for solving this, for getting this characteristic impedance and the propagation constant. So a transmission line has the following parameters, that is R is equal to 2 ohm per meter, L is equal to 8 nanohenry per meter, G is equal to 0.5 millimho per meter, and capacitance is equal to 0.23 picofarad per meter, and frequency f is equal to 1 gigahertz. So we have to calculate the characteristic impedance and the propagation constant. So the formula for the characteristic impedance is Z naught is equal to R plus j omega L upon G plus j omega C. This is 2 plus, you can easily put all these values, and after solving you will get this 181.39 at the angle 8.40 degree. So what is the value of this? You will, after solving this phasor, you will get the value of 179.44 plus J2 is 26.50. Now the propagation constant gamma is equal to under root R plus j omega L G plus j omega C. R plus j omega L, R is nothing but you can put here R plus j omega L, R is 2 ohm per meter. After solving this you will get 2 ohm per meter, and this G plus j omega C. After putting all these values in this equation, j omega C is nothing but you have to find omega is equal to 2 pi f. So you have to put the value of 2 into 3.14 into 1 into 10 to the power 9. After solving you will get this 0.2774 at the angle 79.31, which will be equal to 0.051 plus 0.273, where alpha is this and beta is this. Now coming to the terminated transmission line, so we can consider two cases when load impedance is equal to the characteristic impedance. This is known as a perfectly matched transmission line, and when Z0 is not equal to ZL, it is known as mismatched transmission line. So maximum power will be transferred to the load in case of perfectly matched conditions, and there will be no reflected waves inside the transmission line. So standing wave pattern, combination of incident and reflected wave. So in this case reflected wave does not exist because no reflected wave does not, because there is no reflected wave. So in case 2, when characteristic impedance is not equal to the load impedance, that is mismatched transmission line. So there will be the reflected wave in the transmission line, there will be the standing wave pattern, and the VSWR will be a finite value. So what is the infinite length transmission line? So what is the solution for this? So solution of the voltage and current is V is equal to V naught plus e to the power minus gamma z plus V naught plus is equal to V naught plus e to the power minus j beta z. Here we have considered alpha is equal to 0, alpha plus j beta, alpha is 0, only beta is considered. So I will get here e to the power minus gamma z is equal to V naught plus e to the power minus j beta z. Iz is equal to e to the power I naught plus exponential minus gamma z is equal to I naught plus exponential minus j beta z. Z naught is equal to voltage upon current, so V naught plus upon I naught. Similarly for the at the infinite length or V naught minus, you can find the value of V naught minus upon I naught minus by using the same equation. So this is nothing but the characteristic impedance. So here you can see that the voltage expressions are same. Vz is equal to V naught e to the power minus j beta z plus V naught e to the power j beta z. So this is for the length plus this is for length z and this is for length minus z, or you can say this is at V naught is equal to 0 and this is at V naught is equal to at distance z. Similarly we can write here, we can find, or you can say Vz upon Iz is not equal to V naught plus upon I naught plus. Why? Because in this voltage and current equations we have both V naught plus and I naught plus, and V naught plus and V naught minus, I naught plus and I naught minus, which is defined at the distance Z naught. And similar, and this V naught, this characteristic impedance is nothing but V naught plus upon I naught plus is equal to V naught minus upon I naught minus. So in this way we can define the characteristic impedance. Now what is the reflection coefficient? Reflection coefficient, similarly we can define gamma is equal to V naught minus upon V naught plus, by assuming that at load, by assuming that the load is at Z is equal to 0. So Vz is equal to V naught plus e ki power minus j beta z plus V naught minus e ki power j beta z. And what will be the value of Iz? Iz is nothing but I naught plus e ki power minus j beta z plus I naught minus e ki power plus j beta z. So what will be the value of I naught? I naught is nothing but V naught upon z from the previous equation. And what will be the value of V naught? I naught minus will be equal to minus of V naught minus upon Z naught. So I have written here V naught minus upon Z naught e ki power plus j beta z. At the load at Z is equal to 0, V0 upon I0 is equal to Z naught V naught plus upon V naught minus V naught plus minus V naught minus. This is nothing but load impedance ZL is equal to Z naught 1 plus, here what we have done, we have taken V naught plus common because we have to define this gamma in terms of gamma. The gamma is V naught minus upon V naught plus, so we have taken V naught minus gamma upon V naught plus, this is again V naught minus 1 minus V naught minus upon V naught plus. So this is 1 plus gamma upon 1 minus gamma at Z is equal to 0. So you can write at length L, we have defined here the deflection coefficient. So the load impedance will be equal to the characteristic impedance multiplied by 1 plus reflection coefficient upon 1 minus reflection coefficient at length 0. And where reflection coefficient at load is equal to Z load, gamma load is equal to gamma 0 is equal to ZL minus Z naught upon ZL plus Z naught. So this is all about the brief introduction of the transmission line. So I will continue with this transmission line in the next lecture. Thank you.